Alrighty, welcome back to operating systems. So, we're done, pretty much. So, do a quick course recap unless anyone has any questions they want me to solve initially. Other than that, we can start by doing a quick course recap to get our review juices flowing, I guess. So, there's also tons and tons of past exams on my website with solutions. On Discord, I posted the latest two that are blank, so we can have those. They're all loaded up, ready to go. But before we do that, let us do the whirlwind review session. So, started off talking about, hey, what's the role of an operating system? It's got to manage resources. So, the operating system lives somewhere between the hardware, it interacts directly with hardware, and it enables applications. So, any of the programs you wrote in 105, they're all running in user mode, they're applications. In 243, you did more hardware stuff, and then in this course, you figured out how to tie them together through the use of an operating system. So, we sit in the middle. So there's three core operating concepts we visited during all of our adventure together. First one was virtualization. Share one resource by mimicking it, aka it has multiple independent copies. We did that with virtual registers for for threads. We did that with virtual memory for processes. We did that with virtual machines for virtual machines. So we virtualized everything. Then we talked about concurrency. That's where things got real fun for us, right? So we have to be able to handle multiple things happening at the same time. We have to make sure things are ordered correctly using center fors or condition variables. We also want to make sure there's no data races. So two concurrent accesses to the same location with at least one being a write is grounds for a data race. So we also need to prevent those through things like mutexes. Then finally, we touched on persistence, how to retain data consistency even without power, and figured out how our file system was laid out, how it maps to inodes. Hopefully you're done with Lab 6. So how directories are represented, how we actually store files on disks. So started off talking about CPU modes. They are actual physical limitations on your CPU that tells you what instructions you can access. I guess all the categories are blanked out here, oops. But this is machine mode. So machine mode, that is where your bootloader firmware live. We didn't really touch on that. We just assume we can get booted. Then there was hypervisor mode living at this level. That controls all of the virtual machines. Then there's supervisor mode or kernel mode. That's where the kernel lives. That actually lets us talk to hardware. And then there is user mode, so that's where applications and libraries live, like the standard C library or whatever library you use, all running at user mode. So, went over some different architectures for the kernel. A monolithic kernel runs all the operating system services in kernel mode. So, it's called monolithic because anything that even remotely touches the hardware all lives in kernel space. So, the kernel has to do virtual memory management, otherwise we'd have no isolation, no security, bad things would happen. It'd have to do some process scheduling to figure out which process gets to run, needs to maintain control over the CPU, so that has to be in kernel space. But IPCs in kernel space, a little bit of it needs to be there to communicate between processes, make sure we can't snoop on one each other. But file system and device drivers could be in user space depending on our architecture. In Linux, which is a monolithic kernel, they all exist in kernel mode. So might be bad because more code might lead to more bugs. And if there's a bug in kernel space and someone takes it over, well, they're operating in kernel space, they can do whatever they want, they have your whole computer. So some kernels, the complete opposite architecture of that is a microkernel that tries to run the minimum amount of services in kernel mode. So only virtual memory, process scheduling, basic IPC run in kernel mode, and then user space would have more advanced forms of IPC, device drivers, and file systems. But generally, things don't do this. One reason is that it is slower because, well, in order to even do any file system operations, you have to cross this user space, kernel space boundary, which means a system call, which means slow. So that's one reason to avoid it for performance. But you might argue this one has better security. But most things, for performance reasons, fall more in the monolithic camp, depending. Then we talked about libraries briefly. Applications could pass through multiple layers of libraries. We couldn't really define what an operating system is because an operating system is libraries plus kernel needed to run your application. Different applications have different requirements. So what you might define as an operating system depends on what libraries you use. These 3 different applications use all different types of libraries. They all exist in kernel or user space. So whether or not these libraries are considered part of the operating system depends on your application. Firefox would probably use all of them, for example. So then we got on to processes. So the operating system creates processes, has to maintain process control blocks, including state. We now know a whole bunch of stuff that lives on the process control block, has like a copy of that U context for each thread in it, has a root page table for virtual memory, has a local open file table for all of its file descriptors. So we learn a whole lot about processes, and then also how to create a new process through fork. And it was forking fun, right? Probably not, but. And then we argued about, well, what would we have to do to create a new process? Well, if we want to run a different program, it would have to load that program into memory, reinitialize the process with that context, and start running a different application. That is when that was that exec-ve system call. That's how to run another program. So then we started our awful terminology. So we're responsible for managing processes. Operating system, there is a strict parent-child relationship between processes. For the exam, and of course for life, you should know and identify and how to prevent zombie processes, orphan processes, and things of that nature. Quick, pop quiz, what is a zombie process?
The child died, but the parents didn't clean up.
Yeah, it means a process has been terminated, but it has not been acknowledged. And the acknowledgement is a wait system call. So it's terminated, but the operating system can't clean up its resources. That's why we call it a zombie. And then an orphan, it is as literal as it sounds. It means some process's parent process has now terminated. It now no longer exists. You do not have a parent anymore, so you need a new one. You get reparented, likely to a init. Then we explored basic IPC. Some basic IPC is read and write through file descriptors. They could represent a regular file, your terminal, a pipe, a socket. Doesn't really matter. We just need to know it's something we can read and write bytes from. Then we figured out, hey, they're pretty powerful. The standard file descriptors, we can redirect them. We can change them to different things. We can change together programs. It was kind of neat. And then we discussed signals, basically interrupts for user processes. That's where we added kill to our vocabulary. Kill is the system call for basically sending a signal. So kernel has to handle 3 types of interrupts. That's more hardware details. You don't really have to know about that. So then we got into scheduling because we needed a break from all of the weird children running and being able to run in any order. So we talked about CPU scheduling, looked at a few different algorithms. First come, first serve, the shortest job ones, round robin, whatever. You had a question about this on the midterm. Likelihood of me asking you again is pretty much 0. So don't worry about it. Then we got to scheduling. It got even more complex. We introduced some priority, introduced priority inversion, talked about things more generally. Some processes need good interactivity. Others, maybe you don't care. Maybe you only care about throughput. Then we got into complications about multiprocessors may require per CPU queues, what real time is. We need to have some type of deadline we meet, either in practice or we guarantee it through counting cycles. And then we got into the scheduling algorithm the kernel actually uses called the completely fair scheduler that tries to model that ideal fairness of giving each process its equal share of the CPU. Might be short answer on this, I don't remember. But we didn't do any long questions about it. Then we got into virtual memory, and that was fun. So we used pages for virtual memory translation because we didn't want to translate every single address at once. That would be really, really inefficient. So we divided memory into blocks. We called them pages. They were likely 4 kilobytes. That's generally what they are in systems, but for questions I can ask you they're any size. And since we divide them into these pages, we only have to translate once per page. So we used page tables, which was an array of page table entries. Each page table entry stored a PPN, so what VPN the PPN actually points to, and the page table entry also had flags. At minimum, it would have to have at least a valid flag. So we had this new problem where we argued about, hey, the page tables are always huge. Just one big table for every process, not going to work. And then we got to everyone's favorite topic, which was multi-level page tables. So the entire idea for multi-level page tables is we're going to split them up into different levels, make sure that each smaller page table fits exactly on a page, simplifies a lot of things for us because our kernel can just operate on pages. Some pages might be used for data, some pages might be used for page tables. And in order for us to translate an address on a 32-bit virtual address system, we would need 3 levels of page tables. We figured out, we had the fun calculation to figure out how many page table entries we can store on each page table. That told us how many number of index bits we needed for each level. And then we just divided the address. We'd never have to translate the offset. And then we figured out how many levels we need. In this case, we have 3. In order to use it for our process, we need to be told where the root page table is, so what page it's on. That would be in like an SATP register if we're actually doing the translations. And then to do the translations, right, we'd have to follow all the levels. Based off the virtual address, that would tell us what entry in the L2 page table to pick. That entry would tell us what L1 page table to use. Then we find the entry from the L1 index, figure out the entry, point us to this. Then finally, whenever we hit L0, that gives us our final mapping, figures out where this VPN actually maps to. Yeah?
So what's
SATP was basically the root page table register. So that's what the MMU is going to use to actually start the translation off. Yeah?
So you hold the physical page number of the root?
Yeah, so it holds the physical page table, or physical page number of the root page table, the highest level one, which would be L2. Yeah?
So would each process have its own SATP?
Yeah, so each process would have its own root page table, and then as part of context switching, right, it would have to change that register to point to it. So that's like exactly what you did for lab 3. You returned me a new root page table, and then to simulate context switching, I just changed the root page table to that, which is basically changing that register. All right, so wrapped up page tables, translate a virtual page to a physical page, or addresses if you use the offsets. So the MMU is the hardware that uses those page tables, which could be a single large page table, but that's really, really, really wasteful. If you only have a 16-bit address, then probably it's fine. The kernel simplifies the kernel. Kernel just cares about allocating pages. It could just do it from a free list of pages. Doesn't have to worry about any fragmentation or anything like that. All pages are the same size. We don't really care what they're used for. And then we've talked about multi-level page tables to save space for sparse allocations, because most programs do not use 512 gigs of memory and need that many translations. Then we were like, hey, that's slow to translate every address like that. So we talked about the TLB, or translation look-aside buffer, which is basically just cache for caching all of those lookups, so I don't have to do those lookups over and over and over again. So then we had a brief detour. We explored a question using priority scheduling. We also looked like mmap. Not covered on the exam, don't worry about it. That was just for fun, my sick idea of fun. So then we talked about threads, and then life got complicated again. So threads enable concurrency. We related them initially to processes. They are just lighter weight. They share memory by default. The only thing that's independent for a thread are its registers and its stack. Its stack lives in virtual memory, so you can give pointers to other thread stack. That is generally a very, very poor idea, and you will have probably very, very undefined behavior. So you shouldn't do that, so we should treat our stacks as being independent. Then, while threads do not have a parent-child relationship with each other, threads just live within a process, so a process can have multiple threads. Initially, it just has one at the start, but you can create others after that. If you fork, that new forked process will be a new process, only running one thread that's a copy of whoever called fork. So that's basically how they work. If a process dies, all the other threads die because they live within a process, they don't execute anymore. There's no such thing as orphan threads because they live within a process. There's no parent-child relationship between threads. One thread, you can join on any other thread, as you have probably noted in Lab 4. You could create a thread, thread 1 joins on the main thread, that's fine. By default, threads are joinable, so there is the concept of a zombie thread. So if a thread terminates and you don't join on it, it's technically a zombie thread because you haven't joined on it, you haven't cleaned up its resources. So they need to be acknowledged unless they are detachable threads, in which case, as soon as they terminate, they release all their resources. So both processes and kernel threads enable parallelization. We have multiple cores on our machine. We want them to run in parallel, not just concurrently. So each process can have multiple kernel threads. P threads by default are kernel threads, so each P thread maps to one kernel thread. There's a whole bunch of different ways to map them. Most implementations are either one-to-one, so one user thread to one kernel thread, that's P thread, or many-to-one, which was your Lab 4, which is pure user threads. So that means all of your user threads map to a single kernel thread. The kernel only knows about that one thread. You are just concurrently switching what code that thread executes. For real programs, the operating system has to manage what happens during a fork or signals, and that was, again, if you fork, new process gets created with only one thread that's a copy of whoever called fork. For signals, we didn't argue about because the rule, I mean, it's not a complicated rule, but it's complicated to handle. If you have 8 threads running in your process and your process gets sent in a signal, a random thread handles that signal. You don't get to pick which one, it's random. Then we argued, hey, now we have synchronization issues. Even with concurrency, especially with parallelism, we can have data races where we started off showing that count where it was inconsistent with what we have with a single threaded application. So we took a deep detour also on sockets and ucontext. You don't have to know sockets for the exam. We give you all of the functions you need to know. Don't give you that, they're just IPC. Ucontext, however, is fair game since you used it on Lab 4. So it's basically threads. It's the state of the user registers. You should have had some experience doing that. The question would not be terribly long for that if it does exist. So next one, we got into how to prevent a data race. We argued, hey, we need to have critical sections in our program to prevent a data race. Data race, again, 2 concurrent accesses to the same memory location with at least one being a write means I'm ripe for a data race, which means I might get an old stale value that is no longer valid. So we first talked about mutexes or spin locks. They're the most straightforward lock. They ensure that only one thread can be executing code between a lock and unlock call at once. That's called a critical section. Since only one thread can be doing that at a time, we don't have any data races because only one thing can access that concurrently. If we have to implement it ourselves because we have a little embedded system or we're writing an operating system or something, we need some hardware support to implement locks. So we need to do that compare and fetch or comp and exchange, whatever that was called, the compare and exchange. So we need to do things like that to implement locks. Those are atomic operations, so hardware level, they either all happen or they don't. They're used for using locks, but in future courses, you might use those atomic operations to help your programs run faster. Spoiler alert for 454, if you do end up taking that. So they will come up later as well. So we also need some kernel support if we want to implement locks that are fair and don't waste resources and don't spin. So we need kernel support for putting threads to sleep, making sure they block, and then waking them back up so we have a mechanism to unblock them. Also, we argued that, hey, for performance reasons, maybe we have a lot of readers and writes only happen sometimes, so we ideally want to have lots of readers all go in parallel and only one writer to happen at once. Then you should use something like a read-write lock, which will allow things like that. It's just pthread RW lock. So then we argued about order. That was only to prevent data races, having only one thread executing at a time. Then we were like, hey, what about if we want to have some type of order between threads? Because initially, they're running concurrently or in parallel. We don't know which one's going to run next. It's a Wild West. Can't make any guarantees. So in order to make sure things happen in order, that was way too many orders, we have to use semaphores to do that. So semaphores are basically just a number, an unsigned int, or just a whole number. So they contain an initial value you choose when you initialize them. They have two atomic operations. You can increment it using an operation called post, or you can decrement it using an operation called wait. And the only hitch here is that if the current value of the semaphore is 0, the thread will block until that value becomes greater than 0, so it can decrement it. So that number will never go negative. So that is the only extra thing. They do not prevent data races. You need to also prevent data races. So typically for ordering, you use semaphores. For preventing data races, you use mutexes. Then we got to more, oh, yeah?
So when you post the thread that wakes up, do they wake up in any order at all?
So there's different implementations for a semaphore. So if you do post it, you kind of know that only one that's currently asleep will wake up. So like mutex is a good fair one, they'd be in line and just wake up one. But it depends on the implementation. But for us, we can assume it's fair and it would just wake up one. But of course, there's different implementations with different trade-offs, which makes our life fun as engineers. All right. Then we got into more advanced locking. So we have another tool to ensure order. They were condition variables. Much clearer for more complex conditions. So if your condition depends on just an int or just a certain number of things, semaphores are good. If it's more complicated, then condition variables are good. Condition variables are basically just a queue that you can manage. So you can wait if they have to be tied with a mutex. So if you check a condition and it's false, you can wait. That will put yourself in a queue and block you. And then, well, if another thread does something so that condition is now true, it can now signal you, which will wake up exactly one thread on that queue. Wake it up, it can reacquire that mutex and try again. This is where it had that while loop, so it has to keep checking the condition because we don't know whether or not that condition got changed out from under us before we acquired that lock. Then we also talked about locking granularity, where, well, we're essentially making our code serial, so that's really slow. In order to get good performance, maybe we have parts that don't data race with each other. So we have multiple mutexes. And if we have multiple mutexes, well, if we try to acquire two at the same time, we might deadlock ourselves, which means one is waiting for a lock held by another thread, and that thread is waiting for a lock held by that original thread. So do we have a thing here? So there were 4 conditions for deadlocking. 2 of them we can't do anything about. Mutual exclusion, which means only one thread can be running at the time. For mutexes, that's the whole point. Can't do anything about that. Other one was preemptions, so I can't just take a locked lock away from you. That doesn't happen with default mutexes. You have it until you unlock it, so I can't do anything about that. The only two I can do anything about is the first one being hold and wait. So I have to have a mutex while trying to acquire another one. If I break that, then I won't have a deadlock. That's where we used our try. If we lock the mutex, we try and lock another one, that's where we tried it. If we tried it, we didn't get it, we gave up the original mutex, so we didn't have hold and wait. So we always just yielded when we held nothing. And then the other way to break it is a circular dependency. So if we always acquire locks in the exact same order, in some specified order, we'll never have a circular dependency, so we won't have a deadlock. So that's generally the easiest way to do them, always acquire them in the same order. All right, then we went to disk. We explored two topics, SSDs and RAID. SSDs are more like RAM, except access through pages and blocks. Had that weird thing where you could only write to a freshly erased page, and you could only erase blocks in you could only erase pages in blocks at a time. So those were weird rules. All you have to really know is those weird rules. Probably at best would be a short answer. Might have to work with the OS for best performance, like trim, to tell the SSD, hey, what pages am I currently not using anymore? So it can go ahead and erase stuff while it's otherwise idle. Then we talked about RAID, how to combine multiple hard disks on our machine in different configurations, with a trade-off of tolerating failures and improving performance using multiple disks. So there's RAID 0, which was I don't care, striping, go fast. So more points of failure, but my performance is very, very good. If I have 5 disks, I get 5 times the performance, but I have 5 points of failure. Opposite of that was RAID 1. So RAID 1, everything is exact copy of each other. So as long as one disk survives, I don't lose any data. Then the next ones that are used were RAID 5. So RAID 5 had a disk devoted for parity calculations. So if one disk died, I could always recover. Then RAID 6 essentially has 2 disks for parity. So if 2 disks dies, I can always recover. Might take a while, but I can always recover. And the parity will always be distributed for performance reasons. And then we talked about, hey, we could also combine things like RAID 10, which is RAID 1 plus 0. Not that big of a topic, so don't worry too much about it, but good things to know, especially if you care about your files and you actually want to do that. So then we talked about file systems, how they enable persistent, describe how files are stored on disk. API-wise, we can open files, change the position to read and write at, talked about the global open file table, what file descriptors actually point to. So each process has a local open file table. Those are basically just, the file descriptors are an index into this table. All the entries point to a global entry. So that's why if you fork, the position would be shared. So weird things might happen. Then for file systems and storing files, we argued to store which blocks they're on. We could do it contiguously, which is bad, not going to be used. Linked, so just make it a linked list of blocks. You're like, hey, yeah, sure, that would work, but we'd have some performance issues with that. Then FAT, same idea, it's just a linked list, but all of the pointers are in a giant array, so they're all right beside each other instead of on separate blocks. So we'd get better performance, and the last one was like an array. Yeah?
So when we're learning about these allocation strategies, we're saying that they're all one block, like say, for a fact. But what's the difference between block and page here? Is it still one block is 128 pages?
So here, you talk about, technically I should be saying I/O block, what I/O blocks it's on. Typically, I/O blocks are the same size as a page, so you might just say page just because it's all the same size and same idea anyways. But yeah, so you might slip up. Usually they're called blocks, but most of the time the blocks are the same size as a page. We don't have that many terms. Lots of things are called blocks. Lots of things are called pages. So kind of depends on the context. All right, Then we talked about inodes. Some of you are still having fun with inodes in Lab 6. That's a hybrid allocation strategy. They have greater flexibility over contiguous linked fat or indexed. It's basically indexed, but multiple levels depending on how big that file is. So some entries point directly to blocks. Then we stole an idea essentially from multi-level page tables. For bigger files, we can have it point to a single indirect block. For bigger ones, we can point to a double indirect. For huge ones, we can point to a triple indirect block, and that supports a gigantic file. On Unix, everything is a file. Names in a directory can either be hard or soft links. So the file names, all they are directory entries, name to inode for hard links, and then essentially name to name for soft links, but that name's going to be stored on inode, so there's a little bit of details there that you're going in with Lab 6. All right, then we got into page replacement. Wasn't that fun? So page replacement. I think that was our first half-hour lecture, right? So first half-hour lecture. We did optimal. That was good for comparison, but not realistic. That was assuming all pages are on disk, and we're trying to figure out which ones should go into memory, and then if memory's full, which ones to kick out back to disk to make the illusion that we can use more memory than we physically have. The optimal algorithm looked ahead, predicted the future, and replaced the page that isn't used in the longest. Whole page replacement algorithm aims to reduce the number of page faults. It's good for, optimal is good for comparison, but we can't always go into the future. Did random, actually works surprisingly well in practice because it's not as bad as FIFO. FIFO, first in, first out. It's easy to implement, but it had that weird anomaly where we had less pages or less memory, and we had fewer page faults, which doesn't make any sense. So that anomaly only exists for FIFO. Other algorithms don't have that. We also said, hey, LRU would be a good thing to implement. That is looking at the past, not using or replacing the block that hasn't been used in the longest time. It gets close to optimal, but it's expensive to implement because, well, it has to scan every single block or do a whole bunch of operations during accesses, which is what we want to avoid. So we did the clock algorithm, which was basically an approximation of LRU. You should practice this. This is definitely going to be on the exam. I think I've told you about it like 1,000 times. So this should be of no surprise. So do these steps. I won't even talk about them. You know what to do. All right. Then we talked about kernel allocations. So some memory allocation algorithms. So concepts are the same for user space memory allocation if you have to implement malloc or free. Kernel just essentially just gives the standard C library a whole bunch of memory called the heap, and malloc and free manage that heap for you. So in your C program, there's static and dynamic allocation. Static ones, they're all done when your program loads, don't have to worry about it. For dynamic allocations, fragmentation's a big concern. If you don't know the lifetimes, you don't know the size, and things of that nature. So dynamic allocation returns blocks of memory. Fragmentation is basically wasted space. Any wasted space between blocks is external fragmentation. Any wasted space within a block that the memory manager is dealing with is called internal fragmentation. And first, we had a general allocation strategy which just gave users the exact size block that they requested, so there's no internal fragmentation. There's only external, and we saw 3 general allocation strategies: worst fit, best fit, and first fit. But we probably wouldn't implement any of those. So we saw some more allocation in the next lecture. We saw the buddy allocator that restricts it to powers of 2. So there's a linked list for each individual level. Every time we do an allocation, if it's too big, we split into powers of 2, 1, and its buddy. In order to, reason why we do that, so it's easy to merge them back together. It's basically log n, which is nice and fast. And then if we have all same size allocations, we have the slab allocator, which is basically just an array and a bitmap to keep track of what is allocated and what is not. And again, you're doing that in Lab 6. Then we wrapped up with virtual machines. So virtual machines, again, I did that last lecture, but quick recap, virtualize an entire physical machine. Multiple operating systems all share the same hardware. Provide isolation. Hypervisor is the thing that controls everything. Type 2 hypervisors are slow. They run in user mode. Type 1 are fast. Hardware support, hypervisor mode, which we all have. Could overcommit on resources. Might need to physically move the VM. More complicated things, but things you know they should be able to do. What you should really know is why we use containers, because they have all the benefits of virtual machines without the overhead. We're all sharing the same kernel. Good way to distribute applications that are always run consistently. And you've been using containers for the entire semester, so should know what they are. All right. Whew, that's the entire course, so let me know on Discord what you want to review in our last and final lecture, which will just be review. So again, you can, on my website, there are exams with solutions. CS111 from UCLA, valid, same course essentially. ECE344, same course, should be valid. In Discord announcements, I posted 2 blank ones. I will have them on my iPad for the next lecture. Please use Discord. Tell me which ones you want me to go over, or just next lecture. Just shout at me to go over them. We'll review it. We'll have fun. We'll laugh. We'll cry. Whatever. So just remember,